extrapolated curve would be. It used to be we got greater speed by running the chips faster. And in 2020, we'd be a factor of 10 below. And to some extent, we've compensated for that by multi-core and increasingly by various kinds of accelerators. This makes the computational environment extremely inhomogeneous and much harder to program efficiently. And we really need computational scientists and engineers to help us write better code to deal with these new machines. Now, I'm going to talk about cosmological dark matter simulations and hydrodynamic simulations. Astronomers give us snapshots, and our job as theorists is both in reality and metaphorically to create the movies that connect the snapshots so that we get a coherent physical theory. So this is Volker Sprengel's beautiful visualization of one of the Aquarius simulations. So this is the size of the halo of a Milky Way, and that's the size of the optical galaxy. So the halo is 1,000 times bigger volume. How does this fit into the cosmic web? More or less like this. So this is a slice of the Bolshoi simulation. This is the highest accuracy simulation, but by far not anywhere near the largest. And to give you a sense of what a simulation like this does, let's just look at 1,000th of the volume of the simulation. Actually, there's supposed to be music going with this, but I guess they didn't turn the sound on. But anyway, so you see these filaments, and where the big filaments cross, you get the dark matter halo of a big cluster. So there's the big cluster. And one of the things that we've done with the simulation is we stored 180 time steps, and we determined all the halos in every time step by 3 different methods: friends of friends, BDM, and Rockstar, and then constructed merger trees. And this is what a merger tree looks like just for that one halo. So this is every halo that ends up in that single big halo that I pointed at, the big cluster size halo. This is using Rockstar, Peter Baruzzi's beautiful code. And this is a nice visualization also due to Peter. And these merger trees then allow us to construct galaxies, including all their environmental information. Every single one of those little halos would host a galaxy. And so we've now had a number of different semi-analytic models that are built on the merger trees. So all of those become one big halo at redshift 0. And of course, the merger tree records the history of every halo at every time step. Now, there are many different fairly big simulations. This is from a nice review by Kuhlen, Vogelsberger, and Angulo. We tried in constructing Bolshoi to look for the sweet spot where we get adequate resolution, a kiloparsec resolution, and a box big enough to give us adequate statistics. There's also a box that was run with the same number of particles on the same computer with the same code and the same cosmology. It's 4 times bigger on a side, so 64 times bigger box, so therefore worse resolution, but still pretty good. And from that same review, this shows many of these other simulations. Bolshoi took almost as much computer time, about 6 million CPU hours, as the most expensive of all of these, the Deus one. Of course, we show pictures at many different time steps. This is from a popular article that I was asked to write for IEEE Spectrum. Now, if you look at the 2 key parameters, the normalization basically of the power spectrum versus the fraction of cosmic density in matter, what you find is that there's been some convergence, more or less, with the WMAP, but also there's a sort of a trend of increasing omega m and also increasing sigma 8. And if you extrapolate, you actually get very close to what Planck just released in March of this year. And so we decided we better rerun the Bolshoi simulation. So we just finished rerunning Bolshoi last month, a little over a month ago. Notice that Millennium is more than 8 sigma away from Planck in both of these 2 parameters. So it's hopelessly bad. Although, of course, it was wonderful at the time. So we've now finished, and also there's a large program of these simulations being done with more or less the Planck parameters that Gustavo Yepes is the PI for. So just to show you what difference it makes to increase omega matter quite substantially. So this is the ratio of the number of halos as a function of their maximum circular velocity. And at redshift 5, we have about 4 times as many halos at the highest maximum circular velocity of about 400. At redshift 3, about 3 times as many at the highest circular velocity. So it's a big difference. It's not a small difference. So it's really crucial to do these nonlinear calculations. Now, to compare with observations, one of the simplest methods is you fill all the halos with galaxies according to a prescription that also leads to the correct correlation functions for different luminosity galaxies. And my former graduate student, Risa Wexler, has been pioneering in this. And so this is work that we did with Risa. And one of the nice examples is how often are we going to get 2 satellite galaxies as bright as the Large and Small Magellanic Cloud? And by using this halo abundance matching technique, we can predict the likelihood of having no such bright galaxies, 1, 2, 3, etc. There's strip 82 of Sloan, where we have about 3,000 Milky Way analogs. And of course, we have an enormous number in the Bolshoi simulation, and we're complete to 50 kilometers a second. So we're certainly complete to larger Small Magellanic Clouds. And this shows that, in fact, the black are the observations, the red with almost no errors are from the simulations. And in every case, we have very good agreement. So, so the sky and the simulation look very good. And as I mentioned, we've done various other tests like the correlation functions. Now, another thing that we do with these big simulations is we fill them with galaxies using semi-analytic models. They're supposed to capture a lot of the relevant physics. My own feeling is you should never trust a simulation unless you've got a model that helps you understand the simulation. And you want to have very simplified models that capture the really key physics as well as these fairly elaborate models. And in the latest version of these models, we're including dissipation, and we're including the instabilities in disks that seem to be a major way that you make these elliptical galaxies or these big spheroids in the centers of spiral galaxies. And in our latest semi-analytic models, this is work with my former student, Rachel Somerville, and my most recent finishing graduate student, Lauren Porter. So we are getting all the correct scaling relations for both spiral and elliptical galaxies, and we can predict the numbers separately of disk-dominated and early-type galaxies. We then, having designed the model to work at low redshift, we wanted to see if it also is correctly reproducing this recent data from the CANDELS project, the biggest project in the history of Hubble. And one of the things that they found is that there's these galaxies that become compact star-forming galaxies, blue nuggets we call them, that rapidly become red nuggets. And indeed, the model does that, and it seems to fit the data very well. But what's crucial is that the majority of these are not mergers. They're instead disk instabilities. The most compact objects, this is the surface brightness and the star formation rate, specific star formation rate increasing downward. And these objects over here are almost all disk instability. So the galaxies, I only showed the ones that move through this segment, but they do seem to move just the way the observations indicate that they move. And we also get these slow quenching galaxies, which are mostly disks. Going on to hydrodynamic simulations. So this is a beautiful visualization of a simulation that Roman ran on Mare Nostrum. So to feed a forming galaxy here, you have both small galaxies and also gas flowing in on filaments. This is an example of one of these simulations that where we follow the gas and we store a couple thousand time steps of a forming galaxy. And we're running this particular one was run with 30 parsec resolution. Of course, you can't run those to low redshift without huge computer costs. So we usually stop at redshift 1.5 or so. White stars, colored was gas. So we've run, this is Daniel Severino's work. Daniel was a graduate student with Anatoly Klippin. He's using the ART code. He was a postdoc with my longtime collaborator, Avishai Dekel, and now he's in Gustavo's group in Madrid. So we've run a total of about 100 simulations so far, and we've got another bunch running now. And the latest ones are run at 15 to 30 physical parsec resolution. And they've been rerun, all of them, with a radiative pressure feedback. And we have a paper that tries to, in a very simplified way, account for the key features of the simulation. In order to compare with observations, we need to turn the simulations into images, and we do that using a code that my former graduate student Patrick Janssen wrote together with me and some others, where we track all the star particles. Every star particle, we usually use Sunrise 99, Starburst 99, but you can use any code you like, Griswold-Charlot, for example, to do the SED of each star particle at each time. And then we track, using ray tracing, the light from the stars through the simulation volume, including scattering, absorption, re-emission, all done self-consistently. And we've programmed this on a system of cores plus GPUs and optimized the data flow so that we actually get an extra factor of 10 speed up. And there were various other things that we did that gave us a huge factor over other codes. So this code is publicly available and widely used. And this is an example of face-on and edge-on galaxies. Most of the ultraviolet, especially in the edge-on case, is absorbed and then re-emitted at mid and far IR. And this shows you how pure starlight gets affected. So images get much bigger because of scattering, but also much dimmer, especially where there's a lot of star formation going on, which is enshrouded in dust. Because Hubble now has this 1.6 micron capability, and that's H-band and also other infrared bands with wide field camera 3, as well as the optical bands, which give us rest frame ultraviolet for galaxies at the high noon of star formation, redshifts 1.5 to 3 or 4. So we always have at least 7 bands from the CANDELS survey, the biggest survey in the history of Hubble Space Telescope. They just finished taking the broad regions of data. They're still following up a bunch of supernovae, including one that appears to be at redshift 2.1. So to compare, we take these beautiful images. This is supposed to represent a galaxy in its rest frame, maybe 10 megaparsecs away. And we degrade them by adding noise and convolving with the point spread function appropriate for each filter at the corresponding redshift. So this galaxy turns into this sort of mess. But you do see that there's all these little knots of star formation, clumps we tend to call them. And that's a characteristic feature that we also see in observations. So this is an observed galaxy. This is a simulated galaxy, and this shows how the dust is dimming these bright star-forming regions. We've begun the process of very systematic comparison of the observations with the simulations. These are observations, Sersic index, axis ratio versus radius, and then here's Sersic again now versus axis ratio. And this is the simulations, and the radius range is smaller, but the systematics are very similar. The triangles are clumpy galaxies, and you'll notice that essentially all the galaxies larger than about 3 kiloparsecs radius are clumpy, and that's true in the simulations and in the observations, for example. So this shows that same sort of diagram, specific star formation rate increasing downward, surface brightness to the right. But now this is the simulation, and it shows that the simulation is behaving very much the way that the semi-analytic model did. And that means that we're not being completely crazy in our semi-analytic modeling. So we start with these compact star-forming galaxies, which quench and become these compact red nuggets, we call them. And it's showing exactly the sort of transformation that we seem to be seeing in the data. I want to end by talking about the Agora project. This is a project that was started last summer. Piero and I, Pierre Madao and I, called people who are working on high-resolution hydro simulations of galaxies to come together at Santa Cruz last summer and plan a program where we would compare all the simulations running on exactly the same initial conditions and to as much an extent as possible with exactly the same physics, so that the big differences would only be the different subgrid physics, star formation and feedback, but not other aspects. And we are now a year later, and we've already submitted a long paper that sort of describes in detail what we're doing, and even almost all the codes have now run pure dark matter simulations to verify that it all works. A majority of the steering committee is actually in the room. So initial conditions for the simulations, we use Oliver Hahn's and Tom Abel's music program, which can generate the initial conditions for every code, and also an isolated spiral galaxy created by Agards and Tessier, so that everybody can tune up their codes on a low redshift galaxy, and not have to wait for these big simulations to get down to low redshift. So same UV background, same cooling function, and all of the codes can be analyzed using the YT package, which is a beautiful analysis tool that can also do beautiful visualizations. Version 3.0 alpha has just been released, and that's a fully Octree compatible version of YT. YT also is a front end for Sunrise. So all of these can be turned into images. And we've agreed we're going to store 200 time steps as the codes run. So there's working groups to generate the initial conditions and the other shared astrophysics. And their work is largely in that first paper. And then there's a bunch of working groups to start analyzing the outputs as they become available. This is the first paper, which has now been on the archive for a month. Now, how would we go to exascale? Well, first of all, with 8 initial conditions, 4 halo masses, 10 to the 10, 11, 12, 13, 2 initial condition sets, lots of mergers, not too many, and 10 codes, and 2 tries each, and about 1 million CPU hours to run to redshift 0 for each one on average. That's a 2 million CPU hour project. That's doable today. If we advance understanding of simulated galaxy formation and evolution enough, this could enable a larger project, for example, actually running a 300 megaparsec cube with 300 large galaxies, 3,000 smaller galaxies at this resolution. That's about 100 million CPU hours just to run that one case. That's doable. If we wanted to do a much bigger cube, well, that would be about 100 giga CPU hours. That's a year on a 10 to the 7, a 10 million core machine, or equivalent with accelerators, so not so many cores, which is realistic in a few years. Anyway, this is how exascale could, for example, be used. This is assuming that we learn enough by doing these zoom-in simulations. Maybe we'll have to do a few more zoom-in rounds before we're ready for that. But the idea is to really understand the key processes in galaxy formation, which we're far from being able to do yet. So to conclude, astronomy has a number of advantages over other fields that are moving toward exascale. Our data is clean, it's mostly non-proprietary, it's mostly funded, and the public loves us. There's all these projects like Galaxy Zoo, where hundreds of thousands of amateurs help us out. The challenges facing us are the big data challenge. Once you're at the petascale, it's very hard to move the data, and there aren't a lot of places where you can handle that much data and actually process it. So we're going to have to learn to interact with remote data. And the changing high-performance computer architecture makes it very hard to use our legacy codes and write really good codes that efficiently use these new architectures. And they demand new collaborations between scientists and computer scientists and sort of people in the intermediate zone to develop tools and scientific programmers to convert legacy code and write new codes efficient on multi-core machines with fault tolerance and automatic load balancing, new ways to visualize and analyze big data remotely. We have to train new generations. We have to improve education and outreach. And I've been working with other people in the San Francisco Bay Area, Silicon Valley, and especially at NASA Ames, to try to create a new center for this. Thanks.